Let's look at a simple truss calculation. Our example is going to be a square truss that's receiving a 5 Newton wind load to its top left joint and a 50 Newton force from the top, which is supporting a roof. We are able to split this 50 Newton load into two separate forces on both of our joints of equal value. We're then going to establish a pinned connection on our bottom left joint. And we're also going to have a roller joint on our bottom right, signifying the normal force going vertically. What those mean is that the pin joint is going to have forces that constrain it in both the X and Y direction. And so things are only going to be able to rotate around that joint because this one is locked in place. Whereas my roller joint is only going to be receiving the normal force back up from the ground. We'll then add some more information for our truss so we can refer to it easily as we do the math. So we're going to apply a letter to each of our joints. And then I've also added names for my forces here. And those are reaction force C in the X direction, reaction force C in the Y direction, reaction force D in the Y direction. And you will see these sometimes referred to as just CX, CY, and DY. To solve this problem, we're going to take the following 5 steps. We're going to determine if it's statically determinate, which means that there is a chance for us to reach equilibrium within the truss, so we can do math that will be applicable. We're going to make sure that our moments are all balanced. We're going to make sure that our X forces are balanced, so it's not going from side to side. Our Y forces are all balanced, and so it's not going up and down. And then our last step is going to be the method of joints. To determine static determinacy, we're going to use the following equation here, which is 2J equals M plus R, where J is my joints, M is my members, and R is my reaction forces. When I apply the values in, I have 4 joints. I have 5 members, 1, 2, 3, 4, 5. And I have 3 reaction forces, 1, 2, and 3. I can then realize that it does equal 8. And so we do have a situation where we can do math that will apply in this situation, and this truss will be able to reach equilibrium. To solve for my moments, all of my calculations are going to be based off of my pin support. And so I'm going to look at all the forces that are applied to this, and one, determine the direction that is causing the truss to rotate. So this 5 Newton force is going to try to cause it to rotate in the clockwise direction, where this force on D is going to try to cause it to rotate in the counterclockwise direction. I'm going to set my clockwise rotations as negative and my counterclockwise as positive. So a moment is going to be calculated by utilizing the force, so the magnitude of it, times the distance. And so in this situation, I have 5 newtons, and it's going to be 15 centimeters away. So I have my force and a distance. Over here, I have 25 newtons of force, and then I have 15 centimeters. We're going to only use 15 centimeters because the force must be perpendicular to where my pin support is. So we're going to draw a line out right there to where it would intersect and be perpendicular, and that distance is 15 centimeters. We're also going to have my reaction force D in the Y direction be that magnitude times 15 centimeters. We actually do not calculate for this 25 Newton force here because it's pointing directly at my pinned connection. And so it will not actually calculate into a moment because it doesn't have a distance involved in it. So looking at my 3 moments, We can then apply it here to the sum of the moments equals 0. And my moments are moment A, moment B, and moment D, A, B, and D. And here's their values. And I've converted this to meters. So 0.15 meters times negative 5 newtons, because that is a negative value because it's rotating clockwise. 0.15 meters times negative 25 newtons, that's negative because it's clockwise again. And 0.15 meters times reactionary force D is going to be positive. I can then solve this equation, and what I will realize is that reactionary force D, the one that is my unknown, is a 30 Newton force. I can then apply that to my truss and move further on within my calculations. In this situation, I'm now going to look to see that the sum of my x forces equals 0. So I have two x forces, both on joint A and on joint C. We're going to consider that moving in the direction from left to right is positive and from right to left is negative. And when I sum this out, so I set all of my forces to 0, I have my positive force of 5 newtons plus reactionary force D in the x direction. When I go to solve this, I can realize that reactionary force D is negative 5 newtons. So when I drew this arrow, actually, I picked the wrong direction to apply, but it's important to just add an arrow just so it has a direction and we know that it is a force. And so when I go back to my truss, I'll just flip that around so I can see that this arrow is going this direction and this arrow is going that direction. And it will signify that rather than having the negative sign in front of it, it'll just be more visual for me moving forward in my problem. I'm now going to look at the sum of my y's equaling 0. And I have 4 y forces, which are the two 25s, and we'll consider those to be negative because they're going down. My 30 Newton that I solved for earlier from my moments. And then I have my reactionary force C in the y direction, which is an unknown, and that's what we're going to solve for. I can take the sum of y and set it equal to 0. And then when I add my two negative 25s to my 30 newtons to my reactionary force C in the y direction, I can then solve it and get 20 newtons. I'll apply that to my calculation, and I can now see that all my external forces that are applied to my truss are now solved. So I can move forward and look at the internal forces and see how they're working within my truss structure. And to do this, I'm going to use the method of joints, which means I'm going to look at each individual joint by themselves and determine if those are balanced by themselves and then move forward. What that's going to look like is this. All of my members now have been replaced by forces that are just being passed through the members between the joints. And it's important to realize if I'm pushing from A onto a board in this situation, it's going to have that C is also pushing on it. So you're going to receive the force in both directions. So if I compress from this side, it's going to be compressed from that side. And tension will be the same way. Whereas if I was pulling up on A, I would have an arrow going the other direction. And I would also see that I was pulling down on this, which would cause the arrow to go in the other direction too. So let's look at just A. In A, this is a rather easy one to solve, and I'm looking to have both my x and my y both summed to 0, so all of my forces being balanced. And while I'm going through this problem, I'm going to keep track of all my calculations up here in the right corner. So I have a negative 25 newtons going down, and I have AC going up, and I don't know that's value. I can assume very quickly that it's going to be positive 25. I have 5 newtons going to the right, which will be positive, and then AB will go to the left as a negative 5. And so I have both of those. The arrow's pointing in towards my joint, and so I will know that it is compression. I can then, within my problem, know that if I'm getting compression from this member to A, it's going to give me compression to B. Also, if I'm getting compression from this joint to A, I know that it's going to be compression to C. And so I can apply those in, and so when I move forward in my problem, I can carry those numbers and values in. In this situation now, I have my 25 newtons coming down and my 5 newtons going to the right. What I'm concerned about initially is that there's nothing actually counteracting this 5 newtons, and so my joint is just going to be continually going off in this direction. But I can realize also that I've not determined the magnitude of my member BC. And so I could realize that it's actually going away from it here, and that there's a component force here that's able to counteract my 5 newtons. And so I'm going to start here and solve for BCX before I move forward, because I know BCX is going to have to be 5 newtons. To do that, my truss is a perfect square, and so I know that the angle here is 45 degrees. And so I can know that the magnitude of BC here is going to be 5 times the square root of 2. I'm also going to know that the component force, if I'm pushing down in this diagonal direction, I am getting 5 newtons of force out this way, but I'm also getting 5 newtons of force down in the y direction. So what that means is I can have my 5 times the square root of 2 in this direction, and then I've got to balance out my y forces, part of that being the component force from my diagonal member here. And so I have 25 going down and 5 going down, having to be counteracted by my member BD. So if I add those two together, I'll get that I need a force of 30 newtons going vertically. I'll then add that into my chart up here, and since it's compression going towards B, I know that's going to be compression going down towards D. And then we'll move forward more. Now looking at the D joint, I have my 30 newtons coming down, and that should be blue, but that's all right. And it's pushing in on joint D, and that's being counteracted by my reactionary force here on joint D, which is also 30 newtons. And since my y is balanced, right, and I only see one x value, I can be comfortable saying that that value of CD is 0. We'll look over at C, although this is solved, just to check into it and to make sure it works out. So in C, I have these values, and I can see that I have 5 newtons here, I've got 0 here, and I don't see anything really counteracting it, with the exception of my tension force coming off here. And so I've got to look at the component force here, which is my 5 newtons here, going away from it, so that does balance it out, right? And I've got the 5 newtons going vertically, counteracting my 25 newtons. And my 5 plus 20 does equal my negative 25 coming down. Let's take a look at our whole structure. What I can see is that all of my joints are now balanced in both the x and y direction, and all of my external forces are also balanced. So I can say that we've completed this, and this truss is in equilibrium, and I can move on.